Okay, welcome back. We're going to finish off the week, today is Friday, by discussing conservation of energy for two specific types of problems. That would be pendulums and springs. Now you know what a pendulum is. There's a picture of a pendulum down here, but you know that a pendulum is simply something that hangs down and moves back and forth. You've seen this multiple times in real life, most likely. Pendulums are an example of a system in which mechanical energy is conserved, so that's why we study them. So, here's what I want you to imagine. Imagine that a pendulum hanging down motionless, that's what you have, so that the bob, which is the part with the mass on it, the part that actually swings back and forth, is just above the ground. That's the name. It's the pendulum bob. Now, at this point, when the pendulum is down, for instance, at point C, imagine this is right above the ground, that pendulum currently has zero energy. There is no energy in that system. The reason it has no energy, well, let's go through the different types. It's just hanging straight down, so it's not moving. And if it's not moving, therefore it has no kinetic energy. Well, if it's just above the ground, it's basically on the ground, just barely above it. If that's true, then there's no gravitational potential energy. With a pendulum, at least in our simple case, where we don't have any springs involved, so I've got no springs involved, so no elastic potential energy. And finally, since there's no friction here, we can kind of discount air friction. It's not sliding over anything. Since there's no friction, there is no internal energy, or Q, yet. Okay? So a pendulum at its equilibrium position has no energy right now. Now, what would happen if someone were to take that pendulum at point C and pull it up to here? Okay? So what that person's doing is, by pulling it, they're producing a force on it, correct? They're pulling it, they're putting a force on it. They are causing it to accelerate from rest, because now they're moving it, so it's got to accelerate some. So there's got to be a force on it, and they're moving it through a displacement. And their force and displacement are not at right angles to each other. Their applied force is probably some sort of direction like this, so the pendulum is getting moved like that. So if there's a force on it, and that force acts over a certain displacement, and those two forces are not, or those two vectors, are not at right angles to each other, we know that that person must have done work on it. And remember what doing work means. Doing work means you are changing the energy of that object or system. Specifically, if we start at C and we pull up to E, and then we hold it at E, you might say initially we've done some work and make kinetic energy because it's moving, but ultimately if we hold it at E, that kinetic energy goes away. What we've really done, what type of energy we really have changed, obviously since it's now up higher, is the gravitational potential energy. Gravitational potential energy of the pendulum has now increased. So we start at C with no energy. By someone pulling it up and back to, let's say, E or A, doesn't really matter which, we could pull it up to here. By doing that, we have given it gravitational potential energy that has increased. So we have given energy to the system. Now we're going to release the pendulum. It swings down. No work is being done, because let's think about the forces that are acting on the pendulum. There's not going to be any work done by an outside force. Remember, those are the applied force, normal, and tension. Once you let go of the pendulum, there's no more applied force. There's no normal force because it's not on a surface. And there is a force of tension, but at point E, look what direction the pendulum is about to move. It's going to move kind of down in this direction, and the tension is this way. That's at a 90-degree angle. Same thing at D. The pendulum right here is moving in this direction, still at a right angle. C, B, and A are all the same. So none of the tension force, even though it is there, does no work. It doesn't give any extra energy to the pendulum bob, to the system. So there's no extra energy being added, which means that the total energy must stay the same. And we know if the total energy is staying the same, it must just be getting converted from one type to another. So if it's getting converted from just one type to another, then what we know, if it starts with potential energy up here, it's losing that as it goes back down to C. All of that initial, okay, so what this means, sorry, I skipped over this part, is that energy is conserved. all the initial gravitational potential energy up here is getting lost because it's moving back down closer to Earth's surface. What does it go into? Well, if it's at rest here, it's a pretty good bet that the pendulum is moving fastest at sea. So where is that energy going? All of the original gravitational potential energy is converted to kinetic energy at the low point in the swing. On the way back up, the reverse happens. All that kinetic energy, it's going to take some energy for that. That object is moving up again, so its gravitational potential energy is going to increase. That energy needs to come from somewhere, so what happens as it swings up? It slows down. The kinetic energy is converted back into gravitational potential energy. Now, this will happen for forever if there is no friction acting on the system. Typically, if I were to do this, there would be some air resistance, yes. So motion would eventually stop. But if there was no friction at all, if no energy is lost due to friction or any any other forces coming into contact with the system, then the pendulum will swing back and forth forever. The fancy physics word for this is oscillate. Okay, oscillate means for something to move back and forth between a set of positions. Okay, that's what oscillate means. There's your word for the day. So, here's what we're going to do. We're going to actually analyze this, and we can actually put some numbers in here. We can actually predict things like the gravitational potential energies at different heights in this motion. Okay, so. Here's the setup. A simple pendulum is constructed of a small ball of mass 1.2 kilograms is attached to a piece of string that is tied to the ceiling. The ball is raised to position A and released. The ball swings through positions B, C, and D on its way to E, where it stops before it swings the other way. Positions A and E are 0.7 meters above position C, and positions B and D are 0.12 meters above position C. Calculate the kinetic and potential energy at each point in the pendulum swing. Okay, so before we calculate for A, B, C, D, and E, let's just take some time to talk about the different types of energy that will be present at all these different points. At A, this is when it just gets released. Remember, it started with zero, with no energy at all. Someone did work on it to raise it up to A. So, what type of energy does it have at A? Well, it's above this kind of zero height right here. And at that point, since it's above that height, it has gravitational potential energy. Now, at point B, it has less gravitational potential energy because gravitational potential energy is measured by m times g times h. The height is lower, so there's less gravitational potential energy. But there's another type of energy. We said that the energy is conserved in the system, so all that initial gravitational potential energy that has been lost from here to here has to go somewhere. Where does it go? Well, obviously, at this point, it is moving, so we now have some kinetic energy because the object is moving. Remember, to calculate kinetic energy, it's 1/2 mv squared. At the very lowest point, it's now just above that zero part, that zero line, so there's now no gravitational potential energy. All of the energy has been converted into kinetic energy. If you look at D, D is pretty much the same thing as B, it's just on the opposite side. Now we have kinetic energy that's decreasing because the object is going higher and it's getting some gravitational potential energy back. In order to gain that gravitational potential energy, it must lose some kinetic energy. So now we have the opposite of what was happening before. The kinetic energy is decreasing, the gravitational potential energy is increasing, and at E, which is exactly the same height as A, this is what we would call the turning point. It stops and turns back. Since it's stopped, it has no kinetic energy, it just has gravitational potential energy left. If you raise the pendulum to this initial height, it can't go past this height on the swing through to the other side unless you were to give it a push or something, unless you were to give it some extra energy somehow. So that's a good example of conservation of energy right there. The gravitational potential energy that it has here, it can't gain any extra energy to the system while it's moving if nothing interferes with it, which means it can't go higher than it was released from. Now, if we're talking about friction, obviously with friction, then we would have something where we would probably lose a little bit of height here, but we're going to assume that there's no friction acting on our pendulum, okay? Now in real life, you can't really say that, but it's fine. For right now, we're just doing the ideal cases. So one quick note before we go and calculate. So at the same height in the system, when the object is at the same height in a system where there's conservation of energy, the amount of energy in different types is the same. Now let me be clear about what this means. What I'm talking about here is just because they're at the same height, the gravitational potential energy and kinetic energy are the total energy at B, the same amount of gravitational potential energy and the same amount of kinetic energy should be there at D. The same exact kinetic energy, the same exact gravitational potential energy. But what you will see, and that makes sense because it's at the same height, there's no difference, just one's on one side, one's on the other. But what you'll see, and a big mistake that lots of people make, are they say that the gravitational potential energy and kinetic energy are the same at these intermediate heights, as in PE here equals the KE here. That is not the case. If you have more than two types of energy, they don't have to be split up the same way, and we're going to see why that is. What you're going to do is you're going to divide your paper into 5 sections. We're going to label them A, B, C, D, and E. Let's figure out A first, okay? So at A, we know we have gravitational potential energy. PEG equals mgh. This pendulum bob has a mass of 1.2 kilograms, gravitational acceleration 9.81 meters per second squared, and a height of 0.7 meters above the ground. If we calculate all these, 1.2 times 9.81 times 0.7, we get about 8.24 joules. That's the gravitational potential energy. Now, when we say at point A, we know that the object is at rest there. That's where it gets released from. So the kinetic energy is 0 joules, and since the kinetic energy is 0, and we know the gravitational potential energy, couldn't we say that we know the total energy? The total energy is just going to be the sum of the kinetic and gravitational energies. Since KE is 0, the total energy for the system must be 8.24 joules. Now that number is going to be important as we move on. Okay, what about for B? B, we know we have 2 different types of energy. It's a little too early to say the kinetic energy because we don't know what the speed of this object is. However, we do know the gravitational potential, or we can calculate the gravitational potential energy because we know the mass and the height at this point. So let's do PEG, once again, equals mgh. PEG equals 1.2 kilograms times 9.81 meters per second squared times, this time the height is 0.12 meters. Well, we find that the gravitational potential energy here is 1.41 joules, okay? Now that's important because if we know the gravitational potential energy, we can use that to find the kinetic energy because we know the total energy hasn't changed. Pendulums are a case, if there's no friction, we're going to assume there's not here. Pendulums are a case where energy is conserved, meaning the total energy of 8.24 joules can't change. If that can't change, then the sum of the gravitational potential energy plus the kinetic energy can't change either. 8.24 joules equals 1.41 joules plus the kinetic energy at this point. If you subtract those two, 8.24 minus 1.41, you find that the kinetic energy is approximately 6.83 joules. Notice what I said. It's not that the gravitational potential energy and the kinetic energy are the same. Okay, they're different amounts, but yet the object has both those types of energy. Its energy is stored two different ways. Okay, at point C ends up being pretty easy because we know the gravitational potential energy, mgh, must be 0 joules because it's got to be 0 because it's right at our 0 line, is right basically on the ground. Again, the total energy can't have changed. No extra work was done on the system once it's been swinging. Gravitational potential energy is 0. The total energy is still 8.24 joules. That hasn't changed. Now the kinetic energy is 8.24 joules as well. So if the kinetic energy increased, what can we infer? The object must have moved faster. And D and E, these are very simple because D is just the same as B, and E is simply the same as A. And the reason that they're the same is because they are at the same heights as B and A, respectively. D has the same height, 0.12 meters, so we would get the same potential energy and the same kinetic energy that we did for B, and likewise for E. The only reason that they're different, I mean, the numbers are the same, it's just that at D, we have gaining gravitational potential energy and decreasing kinetic energy because the object is on the way up. Whereas at B, we had the opposite. Kinetic energy was gaining, gravitational potential energy was decreasing. So, pendulums are actually pretty easy to analyze if you follow the rules. We could even, if we wanted to, find the kinetic energy for, not find the kinetic energy, we already have that. We could find the speed if we wanted for this by simply doing Ke equals 1/2 mv squared. I'll let you guys do that on the homework. I'll be right back with the second part of these notes.